Yes. It's done.
Thank you very much for the invitation and for the introduction. Today I will give a talk on SPH and its application in geotechnical engineering and applied geology. Here it's more like introductory talk, so I will not go very deep in each application examples, but to go do some overview, introduce to the SPH method and its capabilities. So first, the motivation of my research is about the natural hazards. For the most common natural hazards, except earthquake engineering, we can see is that the natural hazard caused by geophysical flows. For example, the debris flows, and also landslide, which means the difference is that the debris flows usually contains more water content, and landslides are more about dry material. So this geophysical flows, we have different type of geophysical flows, and from a modeling point of view, we can have different level of idealization. For example, if it's flat, it can be sufficiently modeled using Newtonian flow models. And if it's mud flows, which means that it is more or less homogeneous or more or less continuum, then we can just use non-Newtonian fluid model or Newtonian fluid model to sufficiently model this kind of flows. In terms of landslides, because the material is geomaterials, if we consider it as kind of continuous geomaterials, then we can use elastoplastic model or viscoplastic model or some hyperplastic model, this kind of constitutive models from the geomechanics to model it. But if this landslide has big stones or some structures inside the sliding body, then the continuous assumption is no longer valid. Then we need to combine continuous consideration and the discontinuous method to model the soil rock mixture. Similar things happens for debris flows. We know that debris flows usually contains water, sand particles, clay particles, and some large rocks, or even part of some trees. So it's a mixture of very complex materials. From a microscopic point of view, or if you only want to obtain some very rough simulations and do some very large-scale simulations, you can sufficiently model debris flow as continuous non-Newtonian fluids. But if you want to simulate some particular phenomena, for example, the size segregation, which means that in a debris flow, the large particles like rocks, it will accumulate on the surface and on the in the front area of the flow. But in the part which is after the front, you will have small particles. So this kind of phenomenon is called size segregation. It is caused because that in dry granular materials, large particles tend to appear on the surface. And in the debris flows, the flow velocity on the surface is faster. So you can see that the large particles tend to accumulate on the front, in the front area. So this kind of things, because it introduces inhomogeneous distribution of materials. So using continuous model is not sufficient. And there are also some other cases. For example, the phase separation caused by the protection structure and the direct interaction with the structures. This kind of phenomenon is highly dependent on the discrete part, that is the large particles. So in this kind of phenomenon, if you want to model it using continuous model, then it would be very difficult and you will miss some important physics here. So we have different level of idealizations, and depending on your selected idealization or assumption, you can choose method of different level of complexity. And to be able to model all of this phenomenon, we need to have some requirements for the method you use. Generally, you need to model the fluid phase and you need to model the soil phase. And if you consider them as some discontinuous coupling problem, then you need to have another method to model the discrete phase, like the large rocks. So the requirement for a method to model these complex geophysical flows in a unified framework should be that it can model fluid phase, especially the violent free surface and the fluid structure interaction. When I talk about fluid structure interaction, I talk about a different level or different types of structure. First, the easiest one is a fixed structure, which you can just model it as a rigid boundary. The second is deformable structure, which means that it can deform under the impact from the fluid phase. And the third kind of structure is a floating structure, which means that it can be considered as rigid body, but its movement is dependent on the interaction. Its movement is not prescribed like boundary condition. So that's the requirement for the numerical method for the fluid phase. And for the solid phase, the method should be able to model large deformation. This is a requirement that compared to the usually used grid-based method like finite end method, because in finite end method, usually to model the solid, we usually use a Lagrangian description, which means that mesh is moving with your material deformation. And sometimes this will cause a problem about mesh distortion, although there are many different methods to avoid this. Like, for example, we can remesh the body so this mesh distortion can be avoided. But sometimes this is very difficult to achieve in 3 dimensions, and it is also difficult to implement, and also it involves longer simulation time. So that's the requirement for modeling of the soil phase. And also the method should be able to include various material behaviors to model different kinds of materials, like mud flow, like debris flow, like dry landslide. So we need to use at least Newtonian model to model soil, to model water, elastic or viscoplastic models to model the solids, and also some non-Newtonian models to model the continuous phase in the debris flows. And if we want to have detailed investigation of debris flows and its interaction with the structures, we need to have discontinuous coupling. So we need to couple the method with discrete end method or multi-body dynamics. And the last requirement, which is usually overlooked, is that for geophysical problems, usually the computational domain is quite large. And if you want to perform a 3-dimensional compute, then the computational cost is very high. And usually you cannot go to large-scale simulations. But to be able to give satisfactory results, you need to find methods to speed up your simulation so it can be used to model large-scale field cases. So that's a requirement for the modeling of geophysical flows in a unified framework. And from my research, I use Sph, and I developed a code which is called Lockit, and it is a uniform GPU accelerated Sph solver for geophysical flows. It can satisfy all the requirements above, and it can model all the type of geophysical flows I mentioned in the last slide. This software, most of the functionalities introduced in this talk are included in an open source version, and you can find the software in the given link. So in the following, I will introduce the application of SPH in different kinds of problems. The first is the SPH for single-phase continuous media. If we want to model landslide debris flows, this kind of geophysics flows using continuous assumption, we have the basic governing equations of these two. That is, this one is the mass conservation equations. It is written in a Lagrangian form, which means that for a material element, its change of density is dependent on its change of volume. So this is this divergence of the velocity field, which is a kind of indicator for the rate of change of the volume. So this is a mass conservation equation, which is a universal principle for all the problems you want to solve in geophysical flows. And the second is a momentum conservation equations, which means that the acceleration of the material element is caused by the net force, which is the internal force caused by the gradient of your stress tensor, and also body force, which is usually gravity in our simulation. For this set of governing equations, the primary unknowns is the density and the velocity. All the other variables, like the location, or the acceleration, or the rate of change of density, or the stress tensors, they can be derived based on the density field and the velocity field. So these two variables, they are selected as the primary unknowns. And what is the solution strategy in SPH? It uses explicit time integration, which means that we use these governing equations if we obtained the status of your system at time step t. And if we can get the status or the solution at time step t plus delta t, then we can repeat this kind of process, and then we can solve this equation in time and space. So your problem can be solved. This is the explicit time integration, and which is used in a lot of numeric methods. The strategy is, for example, at time t, we know all the information like the position, the density, the velocity, and the stress tensor. And based on this, if we substitute all the information into these equations, we can get the rate of change of density and the acceleration, which is this one. And in this part, we need some numerical approximation method to evaluate the partial derivatives, like here and here. So here we need a kind of approximation method or interpolation method. In finite element method, you use a shape function, finite element interpolation. In SPH, you use Sph approximation. It is called Kernel Approximation. And once we obtain these two quantities, we can do the integration to time t plus delta t. And you can just add the increment to the density and velocity, and you get the updated primary unknowns. And using these primary unknowns, you can update the location of the particles of your body, and also you can update its strains. This you need to use some material constitutive models which account for the material behavior, because these two governing equations, they are general for any kind of material and any process. But how can you how can you account for the differences for different material? For example, the water flow and the landslide flow, they obey the same principle governing equations, but the material is quite different. One is water and one is soil. So here, how to compute from the kinematics to get the stress field, then it depends on the material behavior, which is accounted for using constitutive model. So that's the solution strategy here. I only give a very simple example of Euler integration, but in actual computations, Euler integration has low accuracy and low efficiency. Usually we use second order integration method like predictor corrector or valid integration. But I will not give the details here because it is quite common in many explicit many explicit methods. So as I said, to compute the rate of change, we need to have some numerical approximation method to evaluate the partial derivatives in the governing equation. And in SPH, we use a meshness approximation method called Sph Kernel Approximation. Imagine that in your problem domain, you have a kind of kernel function like this, which is spell-shaped and it decreases. It is a radial function and its value decreases if its distance from the center increases. And if we want to approximate a field function, we can write it in this kind of continuous form. You can view this form as a kind of integration, because this is the value or the field value, and this part, this function times this more or less volume serves as a kind of weighting factor. And if you do the integration, you can get the approximated value. But to make this kernel approximation accurate or convergent, you need to have some requirement. First is this normalization condition, which requires that the summation of all the fittings should be 1. This is reasonable because, for example, if you are approximating a constant field function, then this part and this part can be cancelled. Then you have this normalization condition. And the second requirement is a delta function property, which means that when the support domain decreases and decreases, the kernel function should satisfy this delta function property to make your approximation accurate. That is also understandable. For example, if the particle, the place that you want to approximate the field function becomes closer and closer to the center, you will find its value, the approximated value, is closer and closer to the value at this point. So that means this summation of the weighting function here should be closer and closer to the delta function. This too is enough to ensure that the convergence of your kernel approximation. But if you use a infinite large of support domain, you can understand that it means that the material point at one place, it has influence on the material point which is far away from it. This is unphysical in simulations. So we need to limit the support domain, which means that the radius of the support domain of this kernel function should be compact support, which means that it has a radius, which means that the radius is not infinite. And you can give it a radius based on some considerations. Usually the radius is kappa times the smoothing length, And in Sph simulations, we usually use a radius of about, for example, 3 times the average particle spacing. This is a frequently used radius of the support domain. So here we finish the kernel approximation, but what we really need in numeric simulation is the approximation of the partial derivatives. So if we substitute this field function using the gradient of the field function, we can get this equation, which is very similar to this one, just to replace the gradient. But by doing some manipulation or operation, we can reach this approximation form for the partial derivatives. You can see that here, the partial derivative on the field function is transferred to the partial derivative on the kernel function. This is easier because the kernel function is only dependent on the location of your particles or location of your problem of your material element, and it can be easily evaluated. So the computation of the partial derivative is easier. But here you can see that the approximation of the field function and the partial derivatives, they are in this continuous form, which cannot be used in numeric simulation, because here you need to have another method to do the numeric integration. And how to do the numeric integration? In Sph, we just use the Sph approximation, or we call it discrete Sph approximation, which means that for all the points in your support domain, we assign it a volume. The volume is just its mass divided by its density, and for each particle, we sum its contribution in this integration. Then we get this. So the integration here is transferred into a summation. So it's similar here. You can see that this one is the function value, and this one Wij is this kernel function, and here is a volume, which is this dx part. So this Wij times this mj divided by rho j is a kind of a weighting function or shape function, if you consider it from a finite point element point of view. But the thing here is that because we didn't exactly compute the volume from a geometric way, that means, and here we only compute the volume using some very weak considerations, which means here that the summation of all the weighting functions, it is possible that it is not equal to 1, which means that the approximation here is inconsistent. We need to use other methods to correct this. And there are many different methods in Sph to correct this inconsistency and restore the accuracy in approximation. But this method is it's too detailed, and we will mainly introduce the applications here. So if you are interested, you can find my papers or any other papers who deal with fluid simulations in Sph, and you can find the restoration method in the literature. And similarly, for the approximation of the partial derivative, you can write the continuous integration form into the summation form, and then you can compute this partial derivative. Remember that here we need to evaluate the partial derivative of the velocity field and the stress field. And if you substitute the velocity and the stress here, you can get the partial derivatives. So in Sph, we have two forms of approximation. The first form is a continuous form. It is of second order accurate. And the second part of the approximation is a summation, or called discrete form. It is inconsistent. Also, if your support domain is cut by a boundary, then that means the summation of the weighting functions is no longer a unit. Then you also have inconsistency near the boundary. So you need to have special treatment on the boundary. You either extend your computational domain using some boundary particles, or you integrate the missing part in SPH. So boundary treatment is also a very hot topic in SPH research. And with the approximation of the partial derivatives of the field functions, we can transfer this partial derivative equation, partial differential equations, into this ordinary differential equations. So here we approximate this partial derivative using Sph approximation. You can see that here, this is a summation, and here we also write it in a summation. It is a little bit different, but because we use a special method to restore the zeros order consistent. And similarly, for this momentum conservation equation, we write it in this Sph discrete form. This form is, you can say that it is symmetric, respective of the particle index. So here you can see that in this part, you compute the interaction force between particle I and particle J. And here, because this part is symmetric, you obtain the correct interaction force, which means that the computation force from particle I to particle J is the same as the force between particle J and particle I. So you conserve the linear and angular momentum. This is very important in SPH. If you use an unsymmetric form, then your simulation results will become sparse. So these are the ordinary differential equations we need to solve using time integration methods. But are they complete? No, because these are only the governing equations. We also need to consider the material behavior using constitutive models. So the constitutive models, they are used to link the kinematics, which is the motion and deformation, to mechanical responses, that is a stress field. And we need to evaluate the stress from the primary variables, like density and velocity. We consider different kind of geophysical flows. For example, if it's water, we model it in SPH as weakly compressible Newtonian flow, and with equation of state, which means that your pressure can be computed directly from the density. And if it's mud and other kind of flows that can be considered non-Newtonian, for example, lava flows from the volcano, then we can use some non-Newtonian material model like Bingham model, like Cross model, which means that its viscosity is not a constant, but depending on the deformation status or stress status. For example, in Bingham model, you have some kind of yield stress, and after the yielding, you have constant viscosity. But first, your stress needs to pass some threshold, that is a Bingham model. And we also consider elastic solids, which is used to model the structure. We can use linear elastic model or hyperelastic model for small deformation and large deformation. And for solids, especially for geomaterials, we can use the constitutive models from the geomechanics, like the elastoplastic, Drucker-Prague models, and hyperplastic models. And the solution process of SPH in one step, from if you use a predictor correct integration method, is like this. In GPU acceleration, why we use GPU acceleration? GPU is called graphic processor unit. In modern GPUs, used to, for example, playing games, usually you have more than 3,000 computational threads, computation cores. And compared to your modern CPUs, usually maybe you have 8 cores. Although for each core, its computational power is larger than that from GPU, but in total, the computation power of a graphic card is much higher than your CPU. And because SPH, you can say that it is computed using a explicit method. Look at here. You are computing the density and acceleration, density change and acceleration based on some already known variables or quantities, which means that the computation on each particle is independent. So it can be executed by one computational core independently, and there is no interaction or interdependency between different threads. So this kind of structure makes SPH very easy to be parallelized, and its efficiency can be much increased using parallel computing. So that's why we choose GPU for the massive high performance computing. And here the process is that, for example, first you read all the input data and initialize the solver. And because you are machinists, you need to find the surrounding particles to do the computation here, because the summation is over all the particles in the support domain. But the particles in your support domain is always changing. So in every time step, you need to search the particles in the support domain. That is a neighbor search, and you prepare the particle indices, and then do the boundary treatment to prepare the boundary condition, and then do the particle interaction. That is this part to compute the change of density and the change of velocity, which is acceleration. This part usually is the most time-consuming part. And do the integration here. Then we can repeat this in another loop. This is a second-order predictor-correct computation. And all these processes can be accelerated using GPU. And here is a simulation I performed in 2018. And I use a graphic card called GTX 1080 Ti, which was released in 2017 in the spring. And I compare its efficiency with serial CPU computing. And you can see that its efficiency can achieve more than 1,500 times. Usually with this kind of speed up can only be achieved using like supercomputers. But with GPU acceleration, we can get this kind of speed up just using a normal desktop. And the simulation scale can be very large. For graphic card, you usually can model a program with particle number maybe like 40 million if you have 10 gigabytes of memory. So that's the SPH method for single phase continuous media. And in the subsequent part, we will introduce about the applications for a single phase SPH. The first, of course, is the modeling of water flow, which is quite common in the computational fluid dynamics. And we need first to consider the material behavior of water, how you model the material. In SPH, you usually model it as a weakly compressible Newtonian fluid, which means that the stress field can be decomposed into a pressure term and a shear force term. And the shear force is based on the Newtonian assumption that it has a constant viscosity and times this shear strain rate. Then you get the shear force, shear stress, and then the pressure. It can be computed from an equation of states like this. You have the reference density, and if your density becomes larger, then your pressure becomes larger. This is a very simple equation. And integrate this numeric model into the ordinary differential equations, we can solve the system. And a very simple or very common test case for Sph fluid simulation is the Numeric simulation. So you first have a water on the right-hand side and then let it flow, and it impact on some kind of obstacles. And there are some kind of comparison between the numeric simulation and the experiment. We are interested in two aspects. One aspect is the deformation or the kinematics. We measure the change of height, water height at two different points, and we compare the result with the experiment. And we can see that the result, it agrees well with the experiment, except in some area which has very violent free surface. But even in this area with violent free surface, the agreement is reasonably good. And to model, for example, in some cases, you want to know the fluid structure interaction. In that kind of phenomenon, the impact force is very important. So we all measure impact force at a certain point on the obstacle and compare it with the experiment. And we can again find that SPH can give good results in terms of impact force. So it doesn't give correct modeling of the deformation and the kinematics, but also give correct results to the impact force, to the stress and pressure. And the second case, application case for water flow is this water wading. So because I worked in industry, and this kind of problem, because it has a very fragile free surface, and it is very difficult to be modeled using traditional methods. So we use SPH to model this problem of water wading. The intention of this simulation is to find the pressures or the forces on the car body structure to determine whether the car body will have deformation or not. And we also need to find which part of the car body will be occupied by water after the car passes the water plant. This is another simulation of water flow, but because our focus is on geophysical flows, so I will move on from the water flow to other applications. So previously we said that for water simulation, we use equation of state and Newtonian assumption. But if we want to model elastic or elastoplastic solids, we need to use constitutive models to compute stress from the density and velocity. Usually we have large deformation problems, so the computation of stress is usually in this form. So the rate of stress, which means that here we compute the pressure and shear stress directly from the current status. But for solids, usually it's history dependent, so we need to use time integration. And it consists of two parts. One part is a Yeoman stress, which is used to keep the frame objectivity in large deformation. And the second part is a constitutive model based on infinitely small strain assumption. And in geomaterials, we usually use two kinds of constitutive models. One is this hyperplastic model, and the second is the elastoplastic Drag-Braga model. Both of these two models can sufficiently model the deformation of geomaterials, which is very dependent, very different from metals or waters, because it has pressure dependency. What is pressure dependency? It's like if you have metal, your yield stress is independent of your normal stress. But in geomaterial, because of the friction contact, your yield stress is dependent on the normal stress. This is called pressure dependency, which is the most important feature of geomaterials compared to other kind of material. To model other kind of geophysical flows like lava flows or debris flows, we can also use other kind of viscoplastic models like a Bingham model or rheologic drag program model or the new MUM model specifically designed for granular materials. So with this different type of constitutive models, we can model different types of solids or applications in the solid computation. The first and the simplest is a model of elastic bodies. And here is an example we simulate a bar subject to gravity. And under the gravity, it gradually reaches the steady status, and we have the deformation in the z direction. And we can compare the deformation with the analytical solution. And you can see that the result is quite good. And we also investigate the convergence of SPH methods with different kinds of.
I'm interrupting. We are a bit running out of the time. Maybe you need to go on a bit faster because right now we are using the time of the question and answer. But it is very interesting because I see that even the number of the participants are increasing, but I believe that it's maybe better that you go on a bit faster.
Okay, so you can see that with improvements, you can reach second order accurate, like in finite element method. So that's the case for elastoplastic solids. And you can also use different materials to model the large deformation of geomaterials, like the collapse of sand. We can model this in 3 dimensions, and we can capture the phenomenon or the dependency of the final runout and height based on the aspect ratio, which is the ratio between the initial height and the initial width. So SPH can accurately capture this phenomenon. And other applications in single phase continuous media is the slope stability analysis, which we can use hyperplastic model and capture the development of the failure process and get the correct safety factor. We can also use SPH single phase material to model the large deformation, large scale problems. Like this is an example of by the landslide in China. We can simulate this process and match the deposition area and also the time simulation as the development time and also the impact force, which can be measured from some kind of a seismic analysis. This is another example of large-scale simulations. Is landslide happened in China. We use viscoplastic drag program model, and we mark. This is the simulation process. You can see that the landslide happens, and finally it reaches a steady status. We compare the final runout with observations, and this is the deposition height in different sections. You can see that the result is reasonable, but still it cannot very accurately capture the section. So it means that there are some missing mechanisms we will introduce later. And the third part is the SPH for fluid structure or soil structure interaction, which means that, as I explained, there are 3 types of structures. One is fixed, one is deformable, and one is free floating. And we can use the ordinary boundary treatment method to capture the interaction force between the fluid or the material and the structure. So we first extrapolate the pressure field or stress field to the structure and compute the interaction force based on the common SPH formulation. That is the normal SPH momentum conservation equation. And then we do this fluid structure interaction with deformable, structures. Sorry? And also, in this case, we simulate debris flows with debris materials, and we measure its interaction force with the structures, and you can see that the impact force can be captured accurately. If we change the materials into sand, can also simulate this. And here, the important part is the modeling of the solid part, that is the elastic part. Usually in SPH, it is difficult to get an accurate stress field, but with some improvements, you can still get the accurate stress field, and the simulation of the solid, elastic solid, can be achieved. So the first part is the SPH for heterogeneous flows. As we said, there are many different types of geophysics flows, and debris flows is a kind of heterogeneous flows, which means it has a continuous phase, like the mixture of water and clays, and it also have large rocks. So it cannot be really considered as a homogeneous material. And in civil engineering or other engineering, you can also have this kind of phenomenon. For example, the fresh concrete, it has cement, pasta, and aggregates. And in chemical reactor, you can also find the mixture of continuous phase and some large particles. And this is important in geophysics flows, as we said, because there are some unique phenomena like segregation, like arcing of the large particles, and also the interaction between the debris flow and the structures. It cannot be simulated using continuous approach. So we need to model explicitly the impact of large bodies. So we need to use continuous approach and discrete approach. And there are different ways to couple SPH and the fluid solver as a discrete element solver. We can use unresolved coupling, which is usually used in chemical engineering, but the resolved coupling is more accurate, which treats the particles as a boundary of the fluid phase. This is the most accurate way, and we can accurately capture the hydrodynamic interaction force in the resolved coupling. So we develop a fully resolved SPH DEM coupling method. The fluid phase or the continuous phase is modeled using non-Newtonian fluid, and the large rocks or particles is modeled using a method, a specifically designed discrete method, which can handle arbitrary particle shape. We have different ways to represent the particles in DEM. There are multi-sphere method, or level set method, or discrete function representation. But here we have some special requirements in our application. We need first to have arbitrary shape representation, and we want it to be easily, it can be easily prepared. So it needs to have easy pre-processing. And also we wanted to have easy contact detection, so the implementation is simple. And also we want it to be fast, or at least easy to parallelize. So here we develop this surface mesh represented discrete end method. So we first convert the surface mesh into obtain nodes and use these nodes, and with a hybrid contact detection method to compute the contact force between the DEM particles. Here the DEM particles, they are regarded as rigid bodies, and they have a friction contact with each other. And for the contact simulation, we usually have node-to-node contact, which is very simple for like spheric DEM particles. We also have node-to-segment contact. This is a very common contact method in the contact mechanics. But both of these methods, this node-to-node method is not so accurate. This node-to-segment contact method is very complicated to be implemented in 3 dimensions. So we have a hybrid contact method, which means we compute the contact normals based on the particles, not on the segments. And then you can easily identify the contact relation and compute the contact force. So to verify the presented surface mesh represented DEM, we first, for example, go to the park to pick some stones, and we take pictures of the stones, and using a technique called structure in motion, we can get the three-dimensional geometry digitally. And then we make them, we can use it in any kind of the simulations. Here, for example, on the right-hand side, we show parking of the natural rocks. And to verify this kind of a discrete end method, we do a simulation with rotating drums. And in the drums, we fill in different shape of very irregular shape particles. And you can see here we have sphere, we have a tetrahedron, and we have a cross-shaped particles. And you can see that the shape, it has a strong influence on the flow dynamics in the rotating drum. The slope angle of the cross-shaped particles is much larger than the other cases because the interlocking in this particle shape is much stronger. And we also compare the simulation results with the experiments and other numeric simulations, and the agreement is quite satisfactory. So these are other applications. So we model the collapse of a pile consists of irregular rocks. So here we have a library of the rock template, and we randomly pick the rocks to drop it in this cylinder and form this pile, and then remove the cylinder and let it collapse under the gravity. So with this discrete end method, we can efficiently model any kind of arbitrary particle shape. So this serves as a basis for our later development of modeling of debris flows and some other heterogeneous flows. So another problem we need to solve is interaction between the fluid phase and the DEM particles. We need it to be fast, easy to parallelize, easy for processing, and easy to implement in 3 dimensions. And it needs to have decent accuracy. I don't require it to be 100% or 90% accurate, but it needs to give reasonable results in geophysical flows. There are many different ways for the interaction computing between SPH and DEM particles, but they are either very complex in computation and the implementation, or the accuracy is not enough. So here we develop a hybrid contact method, which means that the interaction is also based on the hybrid contact, even its fluid structure interaction. So we use the same contact nodes on the DEM particles and then detect the SPH-DEM contact pair to search the nearest pair and then calculate the contact force. Depending on the material of the material type, we can have different ways to contact the tangential force. If it's fluid, the tangential force is based on viscous force. And if it's solid like geomaterials, the tangential force is based on the friction law. And the normal force is based on the penalty force, which means that if your penetration is larger, then your repulsive force is larger. So with this unified hybrid contact, we can simulate the fluid flow in some kind of a boundary condition to validate the accuracy of this interaction method. So here is a very simple flow with a Bingham model fluid, and it has an analytic solution. And you can see that here we reach the analytic solution quite good, and the velocity distribution is also quite good, except the area near the surface. You can see that because we don't use enough particles in the support domain, there is some errors near the boundary. But as I said, we don't require it to be 100% accurate. We need a decent but fast and easy to implement interaction method to compute the complex geophysical flows. So that means the interaction is also validated. Now we want to simulate heterogeneous flows with a continuous phase and the irregular discrete phase. And we designed 4 different types of particles. One is sphere, one is ellipsoid, one is natural pebbles, I just picked it from the park, and one is tetrahedron. And we let it collapse, and you can see that the influence of the different shape has a strong impact on the flow behavior. And using these 4 different types of aggregates, we form a kind of rich concrete. So here, the blue part is modeled using SPH, which is using non-Newtonian Bingham fluid model to model the fresh pasta of the concrete. And the gray one are the particles. These are the irregular aggregates with the 4 different shapes. So here are the flow. If you release the box, the fresh concrete will flow on the plate. These are the flow behavior of the spheres. And here you can see the flow behavior of the ellipsoid. These are not so different between spheres and ellipsoid. And here are the behavior or the flow status of the pebbles, which are the natural rocks. It is a little bit slower than the ellipsoid and the spheres. And finally, there is the flow of the tetrahedrons. You can see that it's much slower because it stays much longer in the box, and the spread area is much less because of the interlocking between the particles. And here we compare the numeric simulations with experiments. Here the dots are the simulations from our SPH plus this natural rocks, and it agrees well. And we also compare the spread area of different shapes. You can see, unsurprisingly, the tetrahedrons has the smallest spread area, and the spheres and the ellipsoids has the largest spread area. So that's the modeling of heterogeneous flows. And we also simulate because here the continuous phase is modeled using non-Newtonian flows. And here this is a kind of sand rock mixture flow, which means that this continuous phase is modeled using elastoplastic materials. It seems that the video has problems, but you can see it here. So this is just impact. And it's irregular rocks, and the continuous phase, it is sand. And we measure the different impact force if you adjust the different portions of the rocks and the sand, and we investigate the mechanism inside. And the last example is this Hungarian landslide. We already showed in previous part, we model it using pure SPH, but this landslide is actually a soil rock avalanche. So you can see that in previous simulation using pure SPH, we didn't reach very accurate results. So in this large scale simulations, we embedded some rocks inside the body and just let it flow. And the rock has irregular shapes. And here is the result from pure SPH simulation. You can say that the deposition is a little bit different, especially in this area and this area. And we simulate this using the combined method using SPH and DEM. You can see that here the blue ones, they are SPH modeled material, which is the soil, and the gray ones, they are the irregular shape of the rocks. And you can see here, we compare the depth at different sections, and the combined simulation has a better result compared to the pure SPH simulation, which means that it captures the physics in the system, which means in reality, this landslide is a soil rock avalanche, and the influence of the large rocks cannot be ignored. Thanks, and I'm sorry for the delay. And let's go to the question part. The